Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 24, Organic Chemistry 1. Today we will continue with chapter 7, Alkyl Halides, Nucleophilic Substitution and Elimination Reactions. Factors affecting the SN2 reactions. Strength of the nucleophile. First point is, a species with negative charge is a stronger nucleophile than similar neutral species. In particular, a base is a stronger nucleophile than its conjugate acid. Hydroxide is more nucleophile, stronger nucleophile than its conjugate acid H2O, water. Hydrosulfide is a stronger nucleophile than dihydrogen sulfide. Amide NH2- is stronger than ammonia. Second point, nucleophilicity decreases from left to right. So, increasing electronegativity from left to right, the more electronegative elements have more tightly held non-bonding electrons that are less reactive toward forming a new bond. Going from left to right, we will find that amide is a stronger nucleophile than hydroxide than fluoride. We will find also that ammonia is more nucleophile than water. Triethyl phosphine is a stronger nucleophile than diethyl sulfide. Point 3. Nucleophilicity increases down the periodic table following the increase in size and polarizability and the decrease of electronegativity. So iodide is more nucleophile than bromide, more nucleophile than chloride than fluoride. Hydroselenide ion is more nucleophile than hydrogen sulfide than hydroxide. Triethyl phosphine is more nucleophile than triethylamine. Point number 4, bulky groups on the nucleophile hinder its close approach to electrophilic center and slow the reaction rate. For example, ethoxide is a stronger nucleophile than tertiary butoxide. See here, the oxygen O- is surrounded by the methyl group, make it less nucleophile, while here you can see clearly that the O- is more clear and free to attack. Let's try these questions. For each pair, predict the stronger nucleophile in the SN2 reaction using an alcohol as a solvent. Explain your prediction. Diethylamine or triethylamine? Diethylamine or triethylamine? Diethylamine is a correct choice. It's better nucleophile because it's less hindered. It is the same atom, nitrogen, but one with 3 ethyl group around it and one with 2. So this is more sterically hindered. BH3 or NH3. BH3 is better nucleophile because phosphorus atom is larger and thus more polarizable than nitrogen. Dimethyl ether or dimethyl sulfide. Dimethyl sulfide is better nucleophile, again because sulfur is larger than oxygen and thus more polarizable. H2S or H3S minus. It is the same atom, but one with a charge and one is neutral. So H3 methyl sulfide is better nucleophile because anions are better nucleophile than the neutral atoms of the same element. Solvent effect. Protic solvents like alcohol, which has OH, are convenient solvents for nucleophilic substitution because the reagents, alkyl halide and nucleophile, tend to be quite soluble in these solvents. Small anions are solvated more strongly than large anion in a protic solvent because the solvent approaches small ion more closely. So its fluoride will be solvated more than the iodide, make the iodide more free to act as a nucleophile. So we will find in protic solvent that the fluoride is the least nucleophile, followed by chloride, bromide, and the most nucleophile will be the iodide in protic solvent. Protic solvent which can solvate these ions. Okay? Polar aprotic solvent, which is polar but with no OH or NH, have a stronger dipole moment to enhance the solubility to a certain extent. Example for polar aprotic solvent: acetonitrile, acetone, dimethyl sulfoxide, dimethyl formamide. As you can see, in none of them OH or NH. In contrast with protic solvents, a protic solvent without OH or NH enhances the nucleophilicity of the anions. There is no solvation here as the one in protic solvent. That's why you will find that fluoride is the most nucleophile, while the iodide is the least nucleophile. We can add specific solvating reagent to enhance solubility without affecting the reactivity of the nucleophile. For example, we can add crown ether, 18 crown ether, to solvate potassium. So if you have potassium iodide or potassium fluoride, the crown ether will solvate the potassium, making the fluoride free to react. So increase the free fluoride ion in the medium, okay? So it will react with alkyl halide, what we call it halogen exchange, and form the fluoride. Reactivity of substrates. Leaving group effect. A good leaving group should be first electron withdrawing group to polarize the carbon atom bond. Should be electron withdrawing group to polarize the function group. Stable, once it has left. Good leaving group should be a weak base. Therefore, it is a conjugate base of strong acid. The hydrohalic acid like HCl, HBr, HI are strong, and their conjugate bases are all weak bases. Other weak bases such as sulfates, sulfonate ions also are good leaving groups. So here is hydroiodic acid, is very strong acid. Its conjugate base is a weak base. HBr, again pK -9, so it's strong acid, has weak conjugate base. Br-, Cl-, sulfates, H3O+, again a strong acid, weak base, water, conjugate base. Exception, F is typically an extremely poor leaving group. Fluoride is poor leaving group because it forms a strong bond to carbon. It's not easy to leave. Moderate leaving group like acetates, like ammonia, is moderate leaving group, weak bases. For the OH- and methoxy, poor leaving group because it's strong, it is a strong base. Amide, hydride, alkyl anion are extremely poor leaving groups because they are strong bases. Point number 3, polarizable. To stabilize the transition state, to maintain partial bonding with the carbon atom in the transition state. This bonding helps stabilize transition state and reduce activation energy. Iodide ion, one of the most polarizable ion, we call it soft ion, is both good nucleophile as well as good leaving group. In contrast, fluoride ion, what we call it hard ion, poor nucleophile in protic solvent and poor leaving group in SN2 reaction. See, iodide has large size, so it can really polarize easily and form good bonding, okay, in the transition state when it starts approaching the alkyl halide. While fluoride, small in size, it has a little bonding in the transition state, so this is not stable transition state at this one. Steric effects on the substrate. Different alkyl halides undergo SN2 reactions at vastly different rates. The structure of the substrates is the most important factor in its reactivity toward SN2 displacement. This effect on the rate is due to what we call it steric hindrance. Methyl halide. Methyl halides are faster than primary halides, faster than secondary halide. The tertiary alkyl halides do not undergo SN2 reaction. See, the nucleophile has to attack the carbon carrying the halides, and the halide has to go out. Rank the following compounds in decreasing order of their reactivity or the reaction with sodium ethoxide in ethanol. Methyl chloride, tertiary butyl iodide, isopropyl bromide, methyl iodide, ethyl chloride. So we have to keep in mind that we have types of alkyl halides, a relative leaving group ability. So we start, as we mentioned before, methyl halide reacts faster than the primary, than the secondary. So we start with methyl iodide. The leaving group here is iodide, faster than the chloride. So it's methyl iodide, then methyl chloride, then we get to ethyl chloride, leaving group is chloride. Here is isopropyl, much more bulkier, and secondary alkyl halide, bromide. And then we come to the tertiary butyl, which is tertiary, even though it's iodide, because of the steric effect. Okay, this will be the least to react. For each pair of compounds, state which compound is better substrate in SN2 reaction, of course. 2-methyl-1-iodo-propane or tertiary butyl iodide. 2-methyl-1-iodo-propane or tertiary iodide. We have this carbon here is tertiary. And in this case here, this is primary. So this is better substrate. Cyclohexyl bromide or 1-bromo, 1-methyl cyclohexane. Here is the alkyl halide tertiary. Here is the alkyl halide secondary. Of course, secondary is better. Two bromobutane versus isopropyl bromide. This is a secondary alkyl halide, and this is secondary alkyl halide. Here is methyl group, here is ethyl group. For the isopropyl, methyl group and methyl group. So the isopropyl bromide is less steric hindrance and will be faster as a substrate in SN2 reaction. 1-chloro-2,2-dimethylbutane versus 2-chloroputane. Looking for the model, you can see that this carbon is the electrophilic carbon. Building it ball and stick. See, this carbon now is hidden by this group. So the nucleophile will not be able to reach easily. On the other hand, even though this is a primary and this is secondary, you can see this carbon, okay, easy to be attacked. Let's see the ball and stick model. You can see that this carbon can be reached. Okay, that's why the 2-chloroputane will be a better substrate than 1-chloro-2,2-dimethylbutane. Stereochemistry of the SN2 reaction. The nucleophile's electrons insert into the back loop of the carbon's sp3 hybrid orbital in its anti-bonding combination with the orbital of the leaving group. Of course, because the bonding molecular orbital is already filled. Backside attack literally turn the tetrahedron of the carbon atom inside out, like an umbrella caught by the wind. In the product, the nucleophile assumed a stereochemistry position opposite the position of the leaving group originally occupied. We call the result inversion of configuration. Inversion of configuration at the carbon atom of alkyl halide. Here we have the nucleophile attacked from the back, kicking the halide out. This is a transition state, and here is inversion of configuration. Inversion of configuration. This is an example here. Alkyl halide, OH nucleophile, attacked from the back, kicking the Br out. The nucleophile approach gave a transition state, and here we have inversion of configuration. We started with Fs2 bromo butane, and we get R butane 2-ol. So from S configuration to R configuration, inversion in configuration, and Br of course out. SN2 displacement is a good example for a stereospecific reaction. What do you mean by stereospecific reaction? One in which different stereoisomers react to give different stereoisomers of product. Here we have cis, 1-bromo 3-methyl cyclopentane. Cis. KOH will attack on the, this is a leaving group here, Br, so OH will attack from here, forming trans 3-methyl cyclopentanol. When we start with a trans 1-bromo 3-methyl cyclopentane, OH will attack from the back, forming cis 3-methyl cyclopentanol. Now let's get to this question. Draw the perspective structure of Fischer projection for the products of the following reaction. Starting with R, 2-bromobentane reacted with potassium cyanide. You draw it this way, means that you have H in the back, right? That's Br. That's Br. Cyanide will attack from the back. Flip, get the hydrogen in front, and cyanide will be in the back. So hydrogen will be in front, and the cyanide will be in the back. Now, let's see. This is the chiral carbon. This is Br, so it is priority. This is 1. Here we have 1, 2, 3 propyl group, so it's more senior than methyl group. So this is number 2, and this is number 3. The configuration here is R. 1, 2, 3. It's clockwise, so it's R. Now, When the hydrogen in front and cyanide in the back, and of course the Br will be kicked out. The configuration here is S. The cyanide will be in the back and the hydrogen will be in front. Okay, so configuration around this carbon is S. This is S2 methyl pentane nitrile. Recall how we used Fischer projection. Here is 2-bromobutane drawn this way, hydrogen right, Br left, methyl up, and propyl down. Recall to draw it this way, the hydrogen and Br should be in front, and the methyl and the propyl should be in the back. Okay? That's essential to understand. Now to name the compound R or S, we have to take this Fischer projection having the least on this side, this least purity, which means hydrogen, right? Okay. We mentioned before in previous lectures that to do so and to get the same compound, we have to do two exchange. Hydrogen with Br was my first choice, so H in here and Br in here. Then I did change the methyl with hydrogen, so the hydrogen is here and CH3 is here. Now for purity, number 1, number 2, number 3 is going this way. The configuration of this compound on this chiral center R. The cyanide, the nucleophile, will attack from this side to this carbon. The hydrogen will be on the left and the cyanide will be on the right. Okay, once again, we would like to get this hydrogen up here. I did the first exchange. This will be the enantiomer. Then I make the exchange methyl with cyanide. So the cyanide this way and the methyl here. Now the hydrogen in the right position. Now this is senior 1, 2, and 3. So we are going this way, counterclockwise. The configuration is S. For this compound, we have 2 chiral centers. This one, that one. And the alkyl halide will be on this one, where we have the leaving group, Br. When I draw it this way, this means that this is up. This is up to methyl and hydrogen, and methyl and ethyl group are in the back. When we react that with sodium iodide in acetone as a solvent, halogen exchange will take place on this carbon, and we get the iodide on the right, and hydrogen will be on the left. Okay, and here is Fischer projection for that one. Carbon 1, 2, 3, as we mentioned 4 and 5 On 2, it's R configuration. On 3, it is 3 configuration. Now, the reaction took place on carbon number 2 with inversion. So number 2 will, the only one will change to 2s. 3 will retain the same with no change, 3r. We can draw 2r, 3r, 2-bromo, 3-methylpentane this way. Okay? Br is up and the metal is up, these two chiral centers. To clarify, I build a model 3D. Okay? Now, the reaction will take place on this carbon with inversion. So the iodo will be in the back of the plane or my computer screen, and the methyl will be up. Here is a 3D model. Here Br is up, up, that's why HBr. Here is methyl, hydrogen, methyl up, hydrogen up. Okay, but I draw it this way, zigzag line, right? So what will happen to the methyl group? Rotation to make the zigzag up. This was down. Remember, okay? So to make it up again, then we have to rotate around this carbon-carbon bond, and the methyl, because we are rotating it, the methyl will be up. All right. For this particular compound, chiral center with 2 halo, Br and fluorine. The Br is better leaving group than the fluorine. So if we react this molecule with hydrogen sulfide, the hydrogen sulfide will attack from the back of the bromine, kicking out Br out, flipping the umbrella, okay, and form this compound. What's the configuration of this species? Hydrogen in the back already. We have here 1, we have here 2, we have here 3. 1, 2, 3. So the configuration of this is S. Now we have R, still H in the back. 1, 2, 3. 1, 2, 3. We are going this way, so it's R. Okay? See you in the coming lecture. Bye bye.